To Calculus 1 with a discussion of average rate of change, instantaneous rate of change, and limits. Calculus is the mathematics of change. Calculus 1 focuses on differential calculus, that is derivatives, and derivatives describe the instantaneous rate of change of an object. Calculus is very widely used, so in physics you would see velocity and acceleration. Velocity is how fast the position of an object changes. Acceleration is how fast the velocity is changing. In economics, we would see modeling of the stock market and many other things using calculus. In statistics and probability, calculus is absolutely necessary for the background of statistics and probability. Calculus is used in population models as well as models of how disease is spread and so on. But without calculus, there's still a lot we can do. So before thinking about calculus, before thinking about the instantaneous rate of change, let's think about the average rate of change of an object. So here's a quick little example, a pre-calculus example. A car traveled 15 miles in 20 minutes. On average, how fast was the car traveling in miles per hour? So I would like you to actually just try this really quick yourself, pause the video and just do it real quick in your notes, and then we will talk about it in just a moment. Okay, so to solve this problem, you might have said to yourself, okay, I know that distance is equal to rate times time. In other words, the distance traveled is equal to the speed at which I was traveling times the amount of time which I traveled. But I wanted to find how fast the car was going. In other words, I want to find the rate. So to find the rate, I could think about dividing both sides of that equation by time and get rate by itself. Rate is equal to distance over time. And then I could say, okay, I know what the distance traveled was, and I know how much time it was. So the car traveled 15 miles in 20 minutes. And so that's the rate at which the car was going on average over that period of time. But now we can say, well, I wanted miles per hour, so I need to convert to miles per hour. I could say that's equal to 15 miles divided by 20 minutes is 1/3 of an hour. And then I could say, well, I know that dividing by a fraction is the same as multiplying by the reciprocal, so this is 15 miles times 3 over hours. And so this is 15 times 3 is 45 miles per hour. And that would be my solution. On average, this car was traveling 45 miles per hour, and we just needed algebra for that. We didn't need any calculus. Let's consider the average rate of change of a graphed function. So let's consider the graph of g of x below. And g of x is equal to the function 1 minus x squared. What is the average rate of change from x equals -2 to x equals 0? So the average rate of change is equal to the slope of the secant line between x equals 2 and x equals 0. So that slope of the secant line between those 2 points, here is x equals -2. X equals -2, and x equals 0, so here's the function at that point. So the slope of the secant line between those 2 points is equal to the change in y divided by the change in x. If this was like a distance and time graph, then the change in x is usually the change in time, the x-axis, and the change in position would be the y-axis. But here we just have some object changing in some way. So change in y over change in x. In our case, that would be g of 0 minus g of -2, the change in output divided by the change in input. So the input is just 0 minus -2. just because we're writing this in as many ways as possible, we could also think of this as the change in output divided by the change in input. Okay, and so what is that equal to? G of 0, in our case, G of 0, that's the output of the function at 0. So when x is equal to 0, G of 0 is 1. So G of 0 is 1 minus G of negative 2. G of negative 2 is negative 3 divided by the input, still 0 minus negative 2, 0 minus a negative 2, and that's equal to 1 minus a negative 3 is a positive 4, 0 minus a negative 2 is a positive 2, so 4 over 2, 2. The average rate of change is 2, and that's also the same thing as the slope of the secant line. So the secant line between those 2 points, the slope of that line should be a slope rise over run of 2. So for every 1 that it goes over in x, it should be going up 2 in y, and that looks about right. So what if we instead wanted to know the instantaneous rate of change at a certain point? So say we wanted to ask, how fast is the function g of x changing at x equals negative 2? So we're saying here's x equals negative 2. How fast is the function changing at that point? So I would like you to pause and think about how you would approach this for a moment. You could even try some calculations out if you wanted to estimate how fast is the function g of x changing at x equals negative 2. And we'll talk about that together in just a moment. Okay, so we want to know the instantaneous rate of change at x equals negative 2 for the function g of x. We are going to estimate this instantaneous rate of change. And one way that we could do that is to find a value very close to x equals negative 2, like x equals negative 1.9, and find the slope of the secant line between these 2 points. So we could use the same method that we used for the average rate of change to estimate the instantaneous rate of change. And negative 1.9 was just chosen, again, as a value close to negative 2, but we could have also used, negative 1.99 or negative 2.1 or negative 2.01, or, that was just a choice that we made. So what is the slope of the secant line between these 2 points? That's the change in y divided by the change in x, or the change in output over the change in input. So that would be g of negative 1.9 minus g of negative 2 divided by the change in the input, negative 1.9 minus negative 2, the x values. One note is that it doesn't matter whether you put the values on the right first or the values on the left first, as long as it matches. So we could have also done g of negative 2 minus g of negative 1.9 divided by g of negative 2 minus negative 1.9. That would have also been fine. But anyway, we can put in those values, and now we need to calculate them. So if you plugged in negative 1.9 into the function g of x equals 1 minus x squared, we could just on the side say g of negative 1.9 is 1 minus negative 1.9 squared. And either plugging that into a calculator or doing it by hand will give you negative 2.61. So now we have g of negative 1.9 is negative 2.61 minus g of negative 2, which we know is negative 3. We could also verify that by plugging negative 2 into g of x if we wished, divided by negative 1.9 minus a negative, so plus 2. That's equal to negative 2.61 plus 3 is 0.39 divided by negative 1.9 plus 2, that's a positive 0.1. And when we divide by 0.1, that's the same as dividing by 1/10. dividing by a fraction is the same as multiplying by a reciprocal. So that's that's 0.39 times 10, and so that gives us 3.9 for our change in y over change of x for the slope of the secant line between -2 and -1.9. So the slope of the line between those 2 points, sorry that these lines are not really great lines, but you get the idea. Slope here is about 3.9, and this was the slope between the points. Let's see, an x value of -2 and a y value of -3, and the point -1.9 was the x value, the y value is -2.61. So that's the slope between those 2 points. The change in y is the change in the graph of the function divided by the change in x. And this is estimating the instantaneous rate of change at x equals -2, but it is not an exact value for that instantaneous rate of change. Now I'd like for you to think to yourself, how could we get a better estimate? So is there a way to get a better estimate of the rate of change of this function at x equals -2? So pause and think about that just for a moment. Okay, so if we want a better estimate, we could select a point closer to x equals -2. Again, there's many different choices for this, but let's use x equals -2.01. So before we used a point to the right of -2. Now let's use before we used a point to the right of -2. Now let's use a point to the left of -2. So -2.01. If we do that, then again we're looking for the change in y divided by the change in x, the change in output over the change in input. And so that would be g of -2.01 minus g of -2 divided by -2.01 minus g of -2. So change in output divided by change in input. And now we can calculate g of -2.01. G of -2.01, that's 1 minus -2.01 squared. And that will give us a -3.0401. So plugging in, we've got g of -2.01 is -3.0401 minus g of -2 is -3 divided by -2.01 minus negative, so plus 2. And simplifying, this gives us -0.0401 divided by -0.01. So simplifying some more, dividing by a negative by negative gives us positive. Dividing by 0.01 is the same as dividing by 1 over 100. Dividing by a fraction is the same as multiplying by the reciprocal. So this is the same as multiplying by 100. And we get 4.01 as our value. This is the slope of the secant line between these 2 points that are very, 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 very close together. The slope of this line is approximately, so the slope is 4, and that's the slope of the line between these 2 points. X equals 2, or x is -2, x is -2.01. So the slope between those 2 points of the function. Again, this is just an estimate, and it's a slightly better estimate than our previous. Our previous estimate was based on x equals 2, or -2, sorry, and x equals -1.9, a point not quite as close to x. And our slope between those 2 points was 3.9. So if you had to guess, what is this getting close to? When we measure on one side, we got 3.9. When we measured closer on the other side, we got 4.01. Maybe this instantaneous rate of change is getting close to 4. And if you are familiar with calculus, you might have said to yourself, well, I already know what that instantaneous rate of change should be. So with calc, and if you haven't had calc before, don't worry, we are going to learn this, but we haven't done it yet. If you had calculus before, then this is just a quick review. We know that if we're looking at the instantaneous rate of change for g of x is 1 minus x squared, then we can take the derivative of g of x. G prime of x is the derivative of 1, any constant is 0, minus the derivative of x squared is 2x. And then we can plug in x equals negative 2 into that function. G prime of negative 2 is 0 minus 2 times negative 2. 0 minus a negative 4, that's a positive 4. And so the instantaneous rate of change is 4 when x is equal to negative 2. Instantaneous rate of change when x equals negative 2 is 4. And we can see that immediately taking the derivative. Again, we haven't learned that yet. That is something coming up, and we can see that it is so much easier to do this with a derivative than it is with this estimating through algebra. Okay, let's talk a little bit about what the derivative means in terms of slopes of lines. So we saw before that the average rate of change was given by the change in y over change in x. So the average rate of change between 2 points is the change in output of the function divided by the change in input. And we also said that that's the slope of the secant line between those 2 points. Now we're talking about the instantaneous rate of change, and we said that that was the derivative, and we said that that could be estimated by choosing a point close to the point we're interested in and finding the slope of the secant line between those 2 points. So we can estimate it in that way. What are we really estimating? We're estimating the slope of the tangent line to the function. So the tangent line to the line tangent to a function, say g, at a point p, like p equals negative 2, is the line that just touches the curve at that point. So if you think of the phrase off on a tangent, if somebody's going off on a tangent, they just intersect with the conversation at one point and then start talking about something totally different. It works here too. So we intersect with the curve just at one point and then keep going in the same direction, whatever direction that was. So there's the tangent line at x equals negative 2, the tangent line at x equals negative 1, the tangent line to the curve at x equals positive 1. And the slope of the tangent line at the point is the derivative at the point x equals p, and it's the instantaneous rate of change at x equals p. So all these things are the same: the instantaneous rate of change, the derivative, and the slope of the tangent line. So we saw doing that kind of magically up above. The way we're going to be starting to think about this is in terms of limits. So, if we say, what's the slope of the tangent line? Slope of tangent line to g of x, our function that we've been working with. G of x is 1 minus x squared at x equals negative 2, the example we've been looking at. We would say that this is the limit as h goes to 0 of g of negative 2 plus h minus g of negative 2 divided by negative 2 plus h minus a negative 2. Or in other words, that's the limit as h goes to 0 of g of negative 2 plus h minus g of negative 2 divided by negative 2 plus h minus negative 2 plus 2. The 2 and negative 2 cancel out, and we just have h on the bottom. What is h? H is the small difference between the point P and the point close to P. So in our example, like when we did the line between -2 and -1.9, h was the difference between those. So in that case, h is a 0.1. So -2 plus 0.1 would give us -1.9. As another example, when we used -2.01 to estimate, when we did between -2 and -2.01, when we found the secant line between those 2 points, then h would have been -0.01. The difference between -2, the point we're interested in, and the point we're using to find the secant line. So, okay, what does this limit mean? Limit as h goes to 0. So this is the limit as h goes to 0. In other words, the limit as h gets really small. What happens to this quantity, g of p minus g of a point close to p, divided by the distance between p and this point? We're talking about the limit as h goes to 0, as that difference between points gets smaller and smaller and smaller. We saw here that difference was 0.1. Here it was -0.01. That difference is getting smaller and smaller. And what we're interested in is, what is the slope of that line as we're taking closer and closer and closer and closer points to the point P? The slope of that line is the slope of the tangent line at P. It's the derivative at x equals P, and it's the instantaneous rate of change of the function at x equals P. So that's kind of a lot right there. This whole idea might take a while to sink in, and you will have time to let it sink in, because this is basically what Calculus 1 is all about. Understanding things like this, which may seem a little abstract right now, over a period of time, and using this understanding of limits to come to something called the derivative. Once we've got the derivative, we'll have some rules that make things a lot easier. But for now, our focus will be on limits. So for now, we are going to talk about limits, and we're going to talk about them in a more general context before reintroducing the idea of the derivative.